Okay, so today we are going to continue where we were last time and look more at this code here. And in particular, this is very much a mastering the basics. And it may have the appearance of being highly pedantic, but it's been my view that having true mastery of things will often come down to deeply understanding the basics and then expanding from there. So think of it as like this is the foundation of a house, and we are trying to make sure that foundation is really rock solid before we add all these other things. On top of that, what this likely will help you do is investigate potentially really scary pieces of code that other people will kind of back away from, saying, whoa, this is too mathematically heavy for me. I don't want to touch this. And admittedly, I think in my engineering experience as well as research experience, I think a lot of people can shy away from this type of complexity because it is obviously very impactful. And if you get this wrong, then things are going to go sideways in a number of different ways very fast. So we should be careful, but we should also, I think, aim to grow and be better. Before we dive into that, for our quick music update, I am listening to this morning, Imperium, Dream Clinic, these guys, and this is coming in pretty loud. I'm ready to do some serious coding. Got my glasses on. You know it's serious if my glasses come on because it means I'm actually gonna really focus on looking at things. And if I've got my techno music playing. So this is the one I'm listening to. I encourage all of you to get your setup the way that is good for you. And then we're going to dive right in. So grab your caffeine, grab your music, and let's get into this. The other thing I wanted to do today that I feel like can be pretty important, and I feel like not enough of this is done in today's world, is to show you sort of how things happen for real. Like rather than just kind of showing you the end result and have it be all pre-coded, to actually walk you through the process, including my own mental thought process on how I think about these things and how I get to the conclusions. I think that is often more important than the conclusion themselves. It's the whole principle of learning to fish versus just giving someone a fish. So I intentionally am starting this stream with absolutely no idea of how I'm going to do this. There's no code here. I just know I'm going to do something here. And what I want to show is that we can make this faster and keep the semantics essentially the same. And so I want to demonstrate that in some capacity. That's basically what I'm striving toward. So if we go to our little notepad, maybe the thing that we can write down is, this is going to be mastering the basics. And our goal is to quantify the performance of the original code in some capacity. Iteratively improve the structure, presentation to improve the performance, demonstrate the performance improvements empirically. Important. So this is sort of like our research goal question, that type of thing. First, we want to be able to quantify the performance of the original code. And we're going to take some shortcuts just to get to the answer faster. But hopefully you'll be compelled that the shortcuts are, because I'm already figuring out the shortcuts in my head as I'm writing this down. But hopefully you'll agree that the shortcuts aren't necessarily changing the core problem. And then assuming we get convergence on that and consensus that that's fine, then we're going to try to iteratively improve it. But we need this as our baseline. Okay, so let me add some more things. This is our baseline. You generally, whenever you're doing research, or even if you're doing engineering profiling, you want to have a baseline because that helps you understand what the starting point is and then where you're headed. So this is going, the first step is the baseline. The second step is improvement. So yeah, I just wanted to, there's a better way to write this, but I just wanted to be on a single line. And then this is our experimentation. This is sort of the basic approach that one might have for doing just sort of like quick level of ideation for a research idea or an engineering idea. Okay, so that's basically what we're going to try to do. Now we're going to go back over to here, and the most important thing is we want to get this if expression. Okay, I'm just going to type it in. Mentor's a little finicky with, okay, I'm going to try to do this in a way that Visual Studio is not going to complain. Equals 0, C equals 0. I'm just going to call this out. Do I want to call it? No, I'm going to call this rows. Equals 0 and calls equals 0. Okay, let me just check here. R, I, C. Do I have J? I don't have J. Okay. R, I, C, J. Rows calls. Okay, cool. So now R minus 1 plus I is greater than or equal to 0, and C minus 1 plus J is greater than or equal to 0, and R minus 1 plus I is less than, we called this rows, and C minus 1 plus J is less than calls. Okay. I think that's what we got. And inside of this, what we're going to do this in a very sort of simple way. We're going to just have a counter, and inside of this, we're just going to increment our counter. That's all we're going to do. All right. Now we're going to call matrix iterations and okay. We're going to hit compile. It's always amazing to me when we write code and it actually compiles. I just to be totally clear, I've been doing this for a while. I still fully expect, in a very serious way, that anytime I hit the compile button, it won't compile. So um, it warms my heart a little bit. Actually makes me wonder, like, is this actually being included? Why did that not break? Um, and I'm not saying this in terms of like false humility. I mean for real. I expect the code that I'm writing first time to not compile. I just, when you've done this maybe as long as I have, 99% of the time that's the result. So I'm just relying on the data here. Okay. This is our core if expression. Yeah. Yeah, we're gonna have some fun on this. I'm in my mind. I've already moved way beyond ints. I'm already templatizing this code and imagining objects that I'm going to pass into it. That's going to make these operations significantly more computationally intense. And so, like, I should be saying these things as I'm thinking them. So, yeah, that's where my head is going. I've already rewritten this code in my head to abstract type information out of it, mostly so I can create objects that then can overload these operators, and then I can force heavier computational overhead when I invoke them, mostly to demonstrate the point of how how much a minor change of greater than or equal to versus just greater than is. And we can see it concretely when we implement the operators of greater than and greater than equal to. But we don't even need to do that. We can keep it the base type to start with. Again, we generally, my view anyway, is we generally always start sort of as simple as we can. We don't need to templatize this yet. We want to kind of just show the core principle. Okay, so now we have this thing, and we're going to do I think, what do I do? Something like this. I actually did have to quickly look this up. Yeah, this here. Hey, Ivan. Okay, time t. What is this? Current time t. Okay, you want it to be this thing. I'm gonna bring this guy over here to this other screen just so I can keep an eye on it. Okay. Now we're gonna go back over here. We need C time. All right. And then in order to do this, they want us to use this time t. We'll call this start time. And then time. This is going to set the start time. Then we're going to do. And we're going to do end time. And then we're going to say. Is and that's going to be seconds. Okay, seconds. Yeah. Okay. Okay. Let's try to. Okay. So now we're going to build this. And trying to remember the function keys here. Control F5, that should run it. think. Oh, I might have pressed the wrong button. Oh, no. Okay, it's just... Oh, that's debugging it. Okay, 0 seconds. Cool. That's sort of what we expected. Okay. Yeah, I don't need this. We're not debugging anymore. Yeah, okay. Okay, so let's just, I want to be able to run this faster. Okay. Okay, this takes 0 seconds. We kind of expected that. Now, what we're going to do is we are going to add some looping on this. So we'll call this iters. Iter is less than k max. One day I will learn how to type on this keyboard. Really, Visual Studio? Like, I liked them aligned like this. I know you're trying to be helpful, but I think that's easier to read. Okay, and max iterations. Let's set this to 1 million. And so you may notice that I'll do certain things like I'll const these out and I'll put this in the namespace. And notice that took me all of like, what, 7 seconds? So why embed the literals, right? And then as we mess with this, you're going to see that this is going to make it so much easier because we're going to just fiddle with this number here and we're not going to mess with this code, right? So it's just like I'm of the mindset that small improvements in the robustness of software might add maybe 5-10% overhead in your code, but it'll likely yield significantly more scalable and iterable, adaptable design that there's almost no reason to not do simple things like this, right? Just create the namespace and const the literal. Don't embed this in here. It's not that hard. So I'm not trying to get all preachy, but this is a mistake I see a lot of new programmers make. And it's one of those things where I don't think it's a lot of work to add this in place. And I think that the result is, yeah, better code. You're also going to, I think, grow quite a bit. You're not going to necessarily be as stagnated. Like just doing, like you may have to learn a little bit about what is a namespace and how do I do this const thing. And so, but these are small footsteps, right? You can kind of like incrementally grow on these things. Okay, so this still takes 0 seconds. So what we can do is we can just keep adding zeros to this until it starts taking more than 0 seconds, right? This is doing this. And I don't think that the optimizer is on. Oh, did I exceed? Okay. Okay, I think it's complete. Yeah, okay. Truncating. And okay, let's... Now there's multiple ways around this. I'm just trying to think of... Okay, let me walk through what's going on in my head. first, so it's hit the threshold, I think, of a 32-bit integer, which is 4.2 billion or something. So I was trying to force it to be a 64-bit integer with this int long. Maybe if I do it a long int, maybe that's the format that it wants. Okay, it's still not liking that. So in my head, I know that there's like an int 64t type or something that will then force it to 64-bit. So I can do that. I can also fix it by just wrapping this for loop with an outer loop that has the extra iterations. So this sort of mirrors the original code a little bit more. So I'm going to do this way, even though I could do it the other way. Uh, but I just wanted to explain what's going on in my head. So those of you that are watching this are like, oh, so he's got multiple solutions to this already, and he's just picking one. And literally, there's probably a dozen if we thought about this for more than 2 seconds. Okay, so I'm going to say this is the outer, and then I'm going to say outer is less than k outer iterations plus plus outer. And just to be a good citizen, I'm going to use these curly braces, visual code for real. Stop messing with it. And then I'm going to also change this just so it's clear. So as we start to get into the weeds, we know what's going on. Okay. Now, I want to also point out that remember how I was saying if you do these things, this can just make your life so much easier, right? We've already hit the breaking point, and I didn't know we were going to go this way. It just happened. And so now it abstracts out these concepts that are you really don't want to be embedded inside of this code, right? There's like my hope is you can see there's a certain amount of elegance that just naturally emerges when you start to build code with a certain intentionality on robustness. Just that the code will tend toward this certain increased order rather than tending toward increased entropy, because you'll have the right pieces in place where it's like, oh, I have this, so I'll put that here, rather than I'm going to add just one more literal inside of the code and then things are going to like get messy. Okay, so now we're going to build this, and it's built. Now we're going to run this, and now this actually is running. Okay, cool. We've reached 5 seconds. That's great. Okay, now the change that we're making for this control expression is, I don't know that it's going to have like a 2x or 3x performance improvement on it. So what I really want to see is I want to see the milliseconds. And so seconds is not enough, but we have a good running time now. So this is going to take 5 seconds to run, which means that's like 5,000 milliseconds. I just want to see the actual milliseconds. So I'm going to quickly look at how to make this in milliseconds and times C++ milliseconds. Okay, it wants me to use chrono, and I've got a couple different this is, why is this so hard, C++? Like, I love you, C++. I love you, C, but like, it's no wonder people are using Python more, right? If you were to look at what let me just bring it over so you can see what I'm looking at. It's like, okay, so I want to do this thing. How do I do this? Okay, so I'm going to do this get time of day. And then he's, okay, so maybe that's just his thing. There's an easier way. Okay. All right. Yeah, that's duration cast. Huh. Okay. Um, okay. Well, we're going to take this and we're going to drop this in as our mechanism. I think they mentioned using chrono, I believe. And then we're going to do this millisecond. This is going to be start time. Okay. Cool. I know I'm doing the copy pasting thing and you're not supposed to do this. But I'm just being lazy. All right. Now in theory, oh, see, now this is what I'm talking about. This is what I'm used to seeing. Like, yes. Okay. Oh. Just curious. Oh, there's a... Oh, I missed the extra. Okay, cool. Yeah, the reason why I went back is I was like, did I miss that? And so I missed this closing paren on both of those and the semicolon because they were doing some interesting whatever. Okay, so there's no operator that, okay, so it doesn't want to output this difference. Okay, so let's do one more thing. Seconds, diff, and we'll say end time minus start time. And I wanted to do this because I suspect that operation is legal. And then to output this, I'm probably going to need some fancy output conversion to output milliseconds. It's a duration cast. Okay, I think I see. This is this. Okay, so basically what I'm trying to do is figure out how I can take my millisecond thing and plug it into this so it knows what I'm trying to do. Okay. CD chrono. Okay, I am using that. It does not know how to do this. By the way, this is part of the reason why I think some people don't love templates is you get messages like this that can be pretty complicated to parse, and it can feel a little overwhelming, right? It's just like you get kind of overwhelmed by the noise. And the way that I tend to break these down, just the way that I think about it, is most of these things are, it's just walking down the template, trying to do all this various pattern matching and trying to essentially help you get at the crux of the problem. But oftentimes it can be the topmost thing that you need to focus on. And so what it's basically saying is there's no operator less than that matches this operation. Now, what I can't tell is if it doesn't like trying to do this subtraction. So I'm just going to make it simple for it and then say this. And so now it's going to say there's no operator for this diff, and that's fine. What I'm going to do now is I'm going to go back to this code, and I'm going to notice that when I do this, I'm going to have to move this over here because I want to look at this at the same time that I'm going to look at this code. Okay, so I see the clock now, time since epoch, and that's milliseconds. Okay, my big question is, can I drop count on this? And I can. Now, in theory, I think, and just to be clear, what I did there, just so everyone understands, is I was looking at this millisecond class, and I made the assumption that this is this millisecond class. I see that there's this duration cast to millisecond, which tells me that this stuff here is being cast into this millisecond type, which then gives me the intuition, the hint that this is type millisecond. Therefore, I should be able to call the count function method on any milliseconds class. And then if I do that, which is what they're doing here, it should potentially be able to stream this out. That's basically what I was doing in my head, and why I needed to see that at the same time I needed to see this, because I needed to pattern match that this millisecond thing here, I could find the right structure that it matched to in the original code on Stack Overflow to then tell me the missing piece. I couldn't tell initially if it was this time since epoch or the count. I didn't know where to start the method invocation on millisecond. And then after looking at it, it seemed as though it's count. Now, we don't know for sure because we haven't run this, but now we're going to run this and we're going to find out. What we should get is around 5,000 milliseconds as the output if we've done this right, and we do. Okay, cool. So we're making progress. Now, keep in mind, everything that we're doing here, I'm doing blind, right? So you're like seeing me figure this out on the fly, and there's no magic here. It's just sort of very simply breaking down the problem into these small digestible chunks and then iterating as we need to go deeper and deeper down the rabbit hole. Remember, we started just with this simple if expression, and then we're like, does that match this thing? Okay, yeah, it kind of does. Cool. We haven't even messed with these values yet. We'll do that momentarily. Then we wrapped it with this inner for loop, and we fiddled with that to try to make it run slow. And we couldn't get there without exceeding the int 32 constraints on size. So then we had to add this additional loop, which we did and we liked because it kind of mirrors this original structure. And then we were seeing that it was taking more than a second, which was great. But then we realized the second granularity is probably not what we want if we're going to try to show this performance difference, because it may not be at the second granularity where we can see the performance difference. So the next step now, if we go back to our strategy, is we now have our baseline, or we have something like a baseline. So let's say check. Okay, good job, team. We've got that. Now, the next thing we want to do is we want to improve this. Now, before we dive in willy-nilly, right, let's think about this for a second. We're not just going to change this code and make it the more optimized version and then run it. That would be silly. And the reason why that's silly is we're not done yet, and we're going to continue to iterate and adapt. So we want the original baseline intact. What we want to try to understand now is what is the appropriate way to extend this code so that we can see the original and we can see the new version. And this is where we have to start, or we can start to make more informed design decisions, because this code is going to start getting a little bit more complicated. So at this point, let me just walk you through the things that I start to think about. The first thing is I start asking myself, do we want this max iteration function to output the total time in milliseconds that it takes to execute, and we embed these operations inside of max iteration? The reason why this could potentially be helpful is if we have the baseline matrix function be its own function, and then we have an optimized version, then we essentially have the timing mechanisms in those functions, and then we just call in the main function the max iterations and then the max optimized iterations. And then we just output essentially what it outputs. So then this code stays clean and simple. And that could be very useful as we start adding more and more tests, because who knows how many tests we're going to make. And if we have this code here just floating around in outer space, we're going to replicate this and it's going to get bigger and bigger. And then calling these tests iteratively in a sort of an expansive way is going to make this code far more complicated. And I much prefer the code that has complexity be in the code that's servicing the client code, not the client code itself. That allows the client code to add more features and do things any way that it wants. So that's one idea that I have. The second idea is, this seems to make sense to me to do that, but what I think we really want to do is just have something that gives us the start time and abstracts away all of this syntactical mumbo jumbo. It's just like too much. I don't want all this stuff. I just give me the total milliseconds right now, and then do stuff, and then give me the total milliseconds afterwards, and then I figure out what I want to do. So in my mind, I've sort of already made the decision that I want to just have this function or this class, this millisecond class, that's going to maybe do the heavy lifting for me. Is I might... So now what I'm doing is I'm designing the millisecond class in my head, and I'm thinking, for this problem, I generally always want two things. I want a start time and I want an end time. That's sort of minimal. Those things should potentially be changeable, especially the end time. But then I want just like the diff operation to essentially tell me what are the millisecond differences between the end and the start time. Therefore, in my head, rather than having it just be a function that's in outer space, having it be a class that is keeping track of the start time and the end time, and then we just invoke the start method and the end method, and then we invoke the result, then that class does all the heavy lifting. That it makes the code that invokes this code even simpler. So I think maybe we'll do that. Yeah. Now, we could also do this in what I call the interface-driven development, which is this notion that we start programming as if the object already exists, and then we just start invoking the mechanisms to use it, and then it gives us essentially what the design pattern will be, and then we implement it. So this is actually how I think a lot of senior developers will write code, and I personally quite like this. So I'm going to do it this way. So I'm going to say, I'm going to pretend that I have, let's call this the Goju MS. Okay, we'll call it millisecond. Goju millisecond class. And then we'll call this MS. Now, should MS take a start time? I think when the class gets constructed, by default, it should set the millisecond start at construction because it kind of makes sense that that's what it would do. We can still override it and change the start time, but by default, in my head, that's what it's going to do. Then, so keep that in mind because I'm going to come back to that. Then we'll have this invoke its end time, and then we will return the MS count. And then that's going to be output here. And this is going to give us some, we'll just have this be an int, and that should probably work. So notice what I've done is I'm basically figuring out what the interfaces are for this class. I haven't written the class, but in my head, its constructor is going to do the start time. That makes sense to me. Then after I finish this, I'm going to say, you're done now. And then when I'm finishing this function, I'm going to say, give me the count. Give me essentially how much time has elapsed. Let's change this to elapsed time. Elapsed time. I like that more. Okay. And notice we don't have a start. I mean, I could do this, right? But in my mind, it's like, well, that should just be here. Okay. So this is what I call interface-driven development. And there may be another name for it, but now we're going to actually build this class. Okay. So we'll have some stuff here. We'll have some stuff here. This is going to be of this std chrono milliseconds. We'll have a start. Yeah. I do like to have these as separate things. I don't know why, but it just makes it easier for me to parse mentally. Then we're going to have this start method that's going to essentially do what we have here. Just going to do this thing. So it's going to say this, and really it's just going to say do that. Okay. And then it's going to complain about this because it wants us to be using namespace std chrono. Okay. And now it goes away. Okay, cool. Now we're going to implement the end. That's what we called it? Yeah. Whoops. An end is going to basically do a similar thing, except it's going to just do the end. Great. We've got both of these things. That's fun and awesome. And then as we mentioned, the constructor is going to, I'm trying to get fancy. Okay, so what I'm doing in my head right now is I really would like to have the member initialization list be invoked just because it's slightly faster than actually calling the start function. And I could do that. I could just embed it here, but I don't like duplicated code. That really annoys me. And so I'm not going to do that. Instead, I'm just going to have the actual thing here, and I'm going to have it call start. So now you can see, hopefully, what I was describing is that when you construct this, this is going to invoke this constructor. This constructor is going to invoke the start. The start will then set the start, and we don't have to call start. We can call start later on if we want, and it'll keep changing the start time. But again, like, why not just have the constructor do it? And yeah. And again, if they want to call it explicitly, like right after this, they still can, right? We just do this. You can do it. And, um, oh, whoops. Yeah. Sorry about that. Yeah. Okay. So, but we don't need to do this. We can do this. This is going to do what it's supposed to do. Now we need to output the do the elapsed time, and this is our guy to do this. This is a const method because it's not going to mutate. These other two operations, start and end, these are mutating operations, so they have to be non-const. And we try to do const correctness in our code because it's like following functional programming mechanisms of trying to be as side effect free as possible. I think it's generally a pretty good principle. And then, yeah, it's pretty easy. We just do this thing and I'm in my head, I'm already optimizing this, but I'm not going to do the optimization yet because it's going to make the code a little bit more complicated. So I'm just going to keep it into somewhat simple form now until we want to make this a bit more streamlined. Okay, cool. So now we've added our wrapper class for this millisecond thing. Cool. I mean, that wasn't that hard. Again, we're just iteratively making this code better and better. And now what we can do is we can get rid of all of this silliness. And instead, we can go like this, which is going to be great. There we go. Now, if we did this right, okay, cool. Yeah. See what I mean about the, oh wait, what is this warning? Diff count. Oh, you're an int 64. Yeah, that makes sense. Let's do now. I want to be clear. I'm doing something a little bit dangerous here, and you shouldn't necessarily do this. I'm doing this because I'm being lazy. I should probably not do this. But hold on, let me finish my train of thought and let me finish doing this, and then we'll do it the better way. Okay, why is this bad? What I am doing essentially is I'm sort of binding to a platform-specific type here. This leading underscores are giving me the clues that this is essentially bound for this operating system, which is Windows. And I shouldn't do that because then when I try to run this code like on Linux or Mac OS, this is probably not going to compile. So this is bad, but you can see that the warning goes away. So let's just run this code, just see that it actually works, and then let's fix it to make it the more portable type in a second. Hopefully that makes sense. Okay, cool. So it worked, right? We get this output that's approximately the same. It did take a little bit longer, probably, who knows? It could be other things that are running. This is doing quite a bit of iteration now, so we wouldn't expect that those results are going to be constant. Okay, so now the right way to do this is to get the actual standard C++ int 64 type. It's like Yeah, this is what it is. It's what it should be is this. This is the correct type. And I know this, or I think I know this, mostly because I just know some of the stuff with C++. And also the leading underscores are gone. The leading underscores, if you see those, just be careful when you use those because it could indicate it's like platform specific stuff. That's why you'll notice that for my class members, I'll use a trailing underscore. I won't use a leading underscore because I'm trying to respect the rules for C++, saying that leading underscores, single or double, are usually reserved for like libraries and compilers, and I'm not writing that stuff right now, so I don't want to use that. So, but because I'm aware of that rule, when I see leading underscores, I think, oh, this is a compiler, library, something specific. I should not use this. I should use more of the standard stuff. And then to walk you through my processing that I did off screen is I just looked up standard C++ int64 type, and it told me this is what I should use. And I should include this header, which, am I including that? C std int. I don't see it. Okay, cool. Well, we'll add that just to be good citizens. C std int. Okay. All right, great. So now let's go ahead and run this again. And we should get around 5,000. Okay, super. Wonderful. We are making forward progress. Now we have a time measurement class that we're going to use for all of these systems, for the unoptimized and the optimized. And what's great too is keep in mind, like, look how simple this is. Like, and in fact, we can make it simpler. It's a little, I don't know that I want to do this, but I can make it simpler and get rid of this call and just have it invoke this, that we can set the end to some uninitialized value, which we probably should have done anyway. That's actually a bug in the code. We should actually set this to something right now. The end should be the start. Yeah, that's right. Yeah. Okay, I'm glad we went and did this. Now, what we could do is that when we get to elapsed time, if end is equal to start, we can set end to now and then do this calculation. And then it just tells you the elapsed time. And in fact, the truth is, I like that model more. So, because it's just a little bit cleaner of an interface. And so we're going to do that. And we should be able to do it just as simple as saying if end is equal to start, then, ooh, we have a conundrum. This is going to be a compiler error. If you are watching this in the VOD afterwards, feel free to pause this if you want to see if you can figure out what the reason for the compiler error is. For the chat, for any of those of you watching, if you have an idea on why this is a compiler error, I haven't compiled it, but you can see this squiggly. Feel free to chime in if you want to take a stab at it. And I'll give you guys just a few seconds before I tell you why this won't compile. Oh yeah, and I keep forgetting. I think I'm like 20 or 30 seconds into the future. on YouTube. By the way, just as an aside, the reason why I think they do that is if something egregiously wrong happens in the stream, like people accidentally do something, I can't possibly but get it, but bonus points for someone who does. Yeah, okay, cool. Yeah, no, I appreciate the activity, Ivan, at the very least. Okay, so the reason why it's complaining about this is my speculation. Again, I haven't compiled it, but I kind of know what it's doing. Is that this is a const method, which basically means you can't do mutating operations in this. And I did that by design because I was saying elapsed time shouldn't mutate this. It should just tell you essentially what the elapsed time is on this. And so it's enforcing this const correctness. In order for this thing to go away, all I need to do is delete this, and then it's gone. And so now we actually have a conundrum, right? It was correct having this be const because there should be this case where it doesn't mutate the state of this this timestamping guy. But we want this behavior. So now this raises a really interesting question on how we can solve this. There's many different ways to solve this that I've already, I'm starting to enumerate in my head. Let me just walk you through some of them. We can add the const back here, and then that'll bring this back in, and then we can make this mutable. If we create this mutable, this thing is going to go away. Aren't you going to go away? Because don't you... Hey, come on. Do you not understand this? Can I convert this? Okay. So the reason why I thought this would go away is that I've made n mutable. So it should be changeable in const methods. Oh, I see. Okay. So I would need to make this const. Okay. My bad. So what it was doing is just saying, yeah, that's mutable, but this is a const method. This is a non-const method. So now the way to fix that, to propagate the const correctness, is I extended this to end. So it's const correct. And then end, the member variable, can still change in a const method because it's mutable. Okay, this is one way to do this, but this is kind of a kludge. I don't love this, so we're not going to do that. That's just not great behavior. Another mechanism we can use is we can create two different methods. We can have this method that is like the non-const version, and then we can have a const version which doesn't do this modification to end. We can call this elapsed time with auto end update to let people know this is going to do the elapsed time and it's going to automatically update the end. And so it's going to change stuff. And then we have the original one, which is just, no, it's going to be const. It's not going to update the end. And so you can call this in a side effect free way. This is, I think, slightly better. Because one, it informs the user on what it is we're doing. And so there's probably a better name for this, but I'm kind of being lazy for it. So we're just going to use this temporarily. Okay, let's go ahead and run this one more time to make sure we're where we want to be. That this takes our 5 seconds.
It does.
All right. We are now ready to actually do our optimization. Can you believe it? We've made it this far. Now, there's a bunch of different ways to do this optimization. One of the ways we can do this is we can make this a function and then just have the unoptimized if and then the optimized if. And so just because the code footprint will be smaller, I think we'll go ahead and we'll do that. Yeah, we'll do that. Will we do that? Okay, sorry. Let me walk through what's going on in my head. If we do that, then we have a few different. Okay, this is going to get slightly complicated. If we do that, in order for this if expression to be called, we need to pass all these variables to that function. Which basically means, depending on how you do this, there could be function call overhead. In a way to circumvent that is we can make the function inline, which will inform the compiler that we want to inline the function. So it will not have the function call overhead, but that's just a suggestion that the compiler doesn't have to inline it when we ask it to. In order to circumvent that, we could make a macro that is like a define for this expression that then will do like actual code substitution in line. It will guarantee it does that. But keep in mind, when we use macros should be, generally speaking, last resort. Like, unless your name is like Ursmuff, you should probably not be using macros. They're extremely dangerous. They lack type safety. They're very, very powerful, but like even I tend to stay away from them because if you do have a bug in them, you generally can't debug preprocessor macros because they don't like exist. So like the preprocessor macro, what it does is it like goes through the code and it injects itself in the places where it's called. So when you go to debug it, it doesn't like go to the macro because the macro doesn't like exist. It's just done code substitution in line. So it's very taxing mentally to debug these things. And because they have no type safety, yeah, it's just super dangerous. So that rules out macros for the code substitution, which then means sort of the only kind of obvious way to do this is if you have a function that we can recommend being inlined and the compiler can ignore that recommendation. And then we've introduced massive function call overhead. And that massive function call overhead could become the new main bottleneck because that's going to be called several billion times. And then any optimization that we make to the sub-expression could now become a small part of the actual overhead. So this is my long-winded way of saying that we should probably, just to be safe, do something which is a little against my principles, which is we just do copy paste on this function and we have the original version and then we have the optimized version. Or we'll call this opt1. V1. Okay. And again, I don't generally love doing this, but hopefully the explanation on why we're doing this in this particular case is sufficient for you to see why I'm doing it. I'm not recommending we do this like in practice, but for our test, given the constraints of this is probably just sort of like the easiest, lowest bar for entry, something like that. Okay, so now what we're going to do is we're going to call this max iteration opti v1 right after we call the original one. And notice that we're going to keep the code exactly the same. We're doing this on purpose. We want to essentially see that when we're calling these two methods back to back, which are identical, that they're going to be approximately the same time window to execute. They're probably not going to be identical, but they'll probably be on the order of about 5,000 milliseconds. That's my hope. Okay, so now we have a problem, right? We've got a very interesting problem, is that there's a full, 800 millisecond difference between calling these two, and we've made no improvements. Okay. I expected that we would get some difference. I just didn't expect that it was going to be like a 20%, 25% difference. This means we may need to do some averages. There's many reasons why this can happen. One of the most obvious is it can do certain amounts of code caching, and it's doing like optimized instruction speculation, because it's like the machine is smart and it's figured out sort of what we're doing, and then it sees the signature is going to be similar, so it does like this prefetching. This is just I'm just ideating here. I don't know exactly why it's doing this, but this is one of many possible reasons why that second one was faster. Let's run this again just to see. What we generally will find, though, is that it will reach a peak. There will be a limit of optimizations that it's invoking once it's achieved sort of the most benefit from speculative execution. I suspect it's around 4,500. And the way to test this is we can just call this a few more times. And by the way, this is getting like pretty ugly. And we're going to call them interchangeably like this, so we can see that it's going to be faster regardless of which one it's called. And so what we should see here is it will peak at around 4,500 milliseconds or so for even like the third or fourth executions. Okay, cool. So our intuition on that was right. That's what we're seeing. It just, again, this is generally known as like warming up the cache. So there's an easy way to fix this. What we do is we disregard the first execution, because that's without a warmed cache. So we just drop it. We only start to consider the numbers after that. Now, in this particular case, you'll notice the second, third, and fourth are getting progressively better. This doesn't necessarily have to hold true. And in fact, if we run this again, if we run this over several iterations, there's a good chance that they won't be progressively better every time. There'll be fluctuations. At least that's what I've seen in my own experience doing this kind of thing. It may take us a couple runs. Oh, okay, cool. So we got an example. Is that you can see the second run was fast, the third run was faster, but the fourth run was slower. Okay, so this is cool. We can also do averages of these executions. And so what we're going to do is we're going to warm the cache by calling just this. Okay, and we'll even add a comment here. And I think I was mentioning that I'm a guy that generally doesn't comment code. And so if I, like this whole class, there's not a single comment, because mostly I think that this code is so simple. Like we all understand, right? I think it's pretty simple. But I do add a comment here. Why? Because if I don't add this comment, what likely is going to happen is people that don't understand what I'm doing, including myself, when I revisit this the next time we talk, I'll forget why I was doing this. And I'll be like, why did I do this? This is just so dumb. Like, we should just not have this line of code. But if I have this comment above it saying warming the cache, I know now, oh, right. I was warming the cache. So don't remove this. It's it's funny how sometimes just stating the obvious in a very simple way, like a one line, 3-word comment, can be the difference between people not deleting this line of code versus them, removing it. Okay, now we're going to rerun this, and we are going to just see if we get these 3 numbers to be approximately the same. And they should be ish. They should be much closer now than what we were seeing before. Okay, I like this a lot more. This feels like this is within the realm of some kind of normal deviation of uh, acceptable standard deviation. It's not anomalous like that other space was. Okay, so now what we can do is we can call this original one. Now we can call the optimized one. And for the optimized one, we're going to do just our very simple change. We're going to simply drop the -1 on both of these, and we're going to change this to just this. So we showed last time that this is essentially equivalent, I believe, in that let's just show if it's r -1 is less than or equal to 0 versus r is less than 0, is we're saying that these are equivalent. We're saying that these are semantically equivalent statements. And if we set r equals 1, then r -1 is equal to 0. 0 is greater than or equal to 0. That's true. And then if r is equal to 1, r is greater than 0. 1 is greater than 0. That's true. Okay. And so we're doing basically just a very simple boundaries check. And we're ignoring I because we can just simplify the sub-expression to try to demonstrate that these are semantically equivalent. We obviously would want to do more boundary condition checking for this than just what I've shown. We want to do the boundary on the other side where it's false and it stays false. But hopefully this convinces you that this is semantically equivalent. Okay, so now we're going to run this. And notice that all we changed is just this. Everything else is identical. And we were already seeing approximately, let's say, 100 to 200 millisecond difference that can go either way. That is basically just noise. So we don't know exactly what this is going to do. It may show up as a performance difference. It may not. We're going to find out right now. Okay, so let's take a look here. So we've got the matrix iterations is the first one. Okay, this one. And then we have our matrix iterations optimization V1 where we drop these things. And now what we saw is that the matrix iterations, at least for that run, was faster than the matrix iteration OptV1. Okay, so I'm going to run this one more time and show you these results. And I already think I know why it's doing this, but I want to just see it one more time and then we'll look at it. Okay, so 4,500 and then this next one. Okay, so before I share, this is this is why I like doing really advanced systems engineering and research can be really challenging, because we have an intuition on these expressions, and it seems as though the empirical data is telling us that we're wrong. The question that I have is, like, for the chat, do we think we're wrong here? Like, are we just like highly confused on this? Is anyone have a thought? Like, and we should probably, while the chat's thinking about this, I'm going to just change this so it shows matrix iterations, matrix iterations opti v1. And I want to try to make these, the pedantic OCD in me wants to make sure these are aligned now. 60. Okay, cool. So chat, does anyone have any thoughts that they want to share? I don't know if there's only one person on chat or if it's Ivan's the only courageous person to jump in. But before I chime in on my thoughts, I just want to see if anyone has any thoughts. Like, is our optimization actually a de-optimization? Are we mostly just confused? I mean, I hope not, but it's possible. I also want to say, before we get into the answer on what I think is causing this, I will say that modern CPUs will do optimizations on things like the three numbers that we talked about, 1, -1, and 0. And so they are very optimized for those particular cases. And they could be invoking CPU level, hardware level optimizations, which is part of the reason why this is not showing us the same performance improvements that we might have expected. Okay, cool. I think I've given people enough time. What I anticipate is, before what we saw, we were talking about warming the cache, right? Well, what we did before is we warmed the cache just for max iterations. We didn't warm the cache for max iterations opti. So now what we need to do is either not warm the cache here, or we need to warm the cache for max iteration opti v1. In this first attempt, what we'll do is we'll remove the warming the cache for the max iterations. And then, because these codes are different now, because their actual conditional is not identical, it's not warming the cache, because the operations that it would load into the instruction cache are different. They're not replications of each other. So if we, yeah, that's awesome. Yeah, we're getting pretty deep down the rabbit hole. So the first thing we'll try is we'll remove the warming the cache to see what the performance difference are from max iterations and our optimized version. Then we're going to try adding the warming the cache for both of them. Okay. So now what we see is we're getting approximately the same performance, which is pretty cool. This one's showing 20 milliseconds slower, but again, that could be just noise. And notice, though, that we're not seeing the performance improvement that we thought we'd be getting from this opti. Now, there's many reasons that this could be happening, none of which have necessarily to do with the fact that this is an optimization. And there's ways that we can potentially tease this out. But before we tease that out, let's try warming the cache for both segments of code. And let's just see what this does. I'm mostly doing this just out of curiosity. And then maybe what we'll do is we'll call this a wrap for part. Okay, that's cool. I really do like the warming the cache thing. This is a very powerful technique that you can use to improve the performance of a ton of things. This is so if we've learned nothing else from this episode, I would argue that we can see concretely the results of warming the cache. This can be super useful when you're going to run something that is going to need to have high degrees of efficiency right out of the gate. But there's a period of time where you can set things up before you like open up the floodgates, like before you turn the website on, before you start doing the buffering from Netflix, all that stuff. So instead what you do is you warm things, and then once everything's warm, then you open it up to the rest of the world. And as we can see in this real world example, we were getting approximately, it's like a 20% performance improvement just by warming the cache. And that's based on the experimental data that I have in doing research in systems for quite some time, maybe 20 years. This is not a one-off. This is something you can almost reliably get with von Neumann computing architectures. And again, I'm not using the word von Neumann to sound fancy. I'm trying to differentiate between von Neumann architectures that use a memory hierarchy, like non-volatile memory, volatile memory like RAM, to L3 cache, L2 cache, L1 cache to registers. That's a von Neumann system, as opposed to other systems which are not von Neumann, like GPUs. There could be GPUs that follow von Neumann, but there could also be GPUs, I think, that don't have the same memory hierarchy that you use in CPUs. So the important point is that warming the caches is often a technique that will see performance improvements for von Neumann architectures. If it's not von Neumann, you may not be able to see that performance improvement because the memory hierarchy is different. They don't have the same benefits of warming the cache because the caches are not the same. So this is why I'm trying to be super precise in the language, so you don't think, oh, I'll just warm the cache for machine learning things and then I'll see the same performance improvement for like GPUs. There's a really good chance you won't. But you will if you do CPUs. Okay, so hopefully that makes sense. Did I want to see something else? Okay, I think I want to just take the warming the cache back out, and I want to run this one more time. And then what I think we'll do is we'll call this iteration done. And then we'll save diving in deeper for next time, because we're definitely not done. But I think that we're getting a certain amount of parity here. Now, with any of the experimentation, there's a number of various ablations that we should look at. Like, for example, right now we're running matrix iterations first, and then we're running the opti second. We should invert this to see what we get there. We need to try to elide away some of the noise. And then one of the bigger concerns that we have is we want to make sure that the performance difference that we're seeing is not due to the CPU doing optimizations on these instructions, that it's not doing on these. And a way for us to test that is to instead, as I was hinting at before, start abstracting out some of these types so they're not ints, that they're user-defined types, which is very much like what you would have for the machine learning systems based on the various constructs that you might have for tokens, right? Those can be, largely they're numerics, but there's there are parameters that can kind of constrain them. So what we'll probably do next time is we'll rewrite this as a template. And rewrite this as a template. We'll create our own base type, which is, we'll start as an int, and then we'll progressively make it more complicated, and then we will implement the greater than or equal to operator, and then we'll implement the greater than operator, and then we'll see what the performance differences are. And we'll be able to see concretely what the implementation differences look like, and how we can see, we'll be able to see very clearly that greater than or equal to at its core is 2 operations, whereas the less than operator is 1 operation. And in my head, I can say almost undoubtedly, this one will be more efficient. And my speculation is that the CPU is doing some CPU magic that's making this thing really fast, but it's only because these native types are going to be optimized at this this sort of like this binary rewriting layer. Yeah, where this kind of stuff like if you haven't worked for Intel or NVIDIA or AMD for over a decade, you might not know about some of the hardware magic that happens. Thankfully, I did spend over a decade at least one of those places. And so I've got some insight into some of the crazy advanced stuff that is happening under the hood to make this code execute much faster. So anyway, yeah, that's basically it for this time. Thanks everybody for dialing in. This is super fun. And I hope we all learned something valuable from this, whatever that may be. And we got to see me write code real time and start hacking away at this problem. We've got more work to do, but we're on our way. Okay, Merly Speed.